Hello guys, welcome back to my channel Algorithm Avenue. From our past few videos, we have been discussing about the various problems that we face in neural network and their corresponding solutions. Now, in this video, we'll be discussing about an important feature in artificial neural networks, that is regularization. Okay, now before diving into what actually is regularization, first let's discuss why this regularization came into implementation. Okay, this regularization technique came into implementation to solve the problem of overfitting. Okay, now let's basically see what actually is overfitting and how overfitting affects the weights. Okay, now I have a data set. Now I have divided my data set into training data and test data. Okay, this is my training data and test data. Now I have trained my model on the training data. Okay, now when I train my model on the training data, this is my decision boundary. Okay, when you keenly observe this decision boundary, it is separating the blue and black classes exceptionally well. Okay, means it is giving me around 100% accuracy. Okay, 100% accuracy. Now, when I come to test data, this is my test data and this is the corresponding class boundary. Okay. Now, when you keenly observe this class boundary, you can see that it has made around 3 errors on my right hand side and around 4 errors on my left hand side. Means it is not perfectly dividing my two classes. Okay. This indicates that it has around 70% accuracy. Okay, this by this we can conclude that my model is exceptionally performing well on the training data but not performing as expected on the test data. Okay, now due to this difference, okay, this difference we call it as overfitting. Okay, this difference is called as overfitting. Okay, now due to this overfitting, what actually happens is the weight values are very much high. Okay, in case of overfitting, the weight values are very much higher. Okay, in case of overfitting, the weight values are very much higher. Now, to solve the problem of overfitting, what we can do is we need to reduce this values of the weights. Okay, we need to reduce the values of the weights. Okay, we need to reduce the values of the weights. Okay, the process, okay, listen carefully, the process of reducing the values of the weights from a higher numerical value to a lower numerical value is called regularization. Regularization. Okay, regularization is a process of decreasing the or diminishing the values of the weights from higher numerical value to the lower numerical value. Okay, this is the process of, okay, this is what actually is regularization. Now we'll be discussing how actually is this regularization implemented and how it actually decreases the values of the weights. Now, our aim is to solve the problem of overfitting. How can we solve the problem of overfitting? By reducing the values of weights from higher numeric to lower numeric. Okay, this conversion is called regularization. Okay, now basically in regularization we have three types. Okay, first is L1 regularization, and second is L2 regularization, and third is L1 plus L2 regularization. Okay, in deep learning, mostly we use L2 regularization. So, in this video, our entire focus will be on L2 regularization. Okay, now let's dive into discussion of L2 regularization and how, due to this L2 regularization, the values of the weights are diminished. Okay, now basically see where actually this regularization is actually applied. Okay, now let me consider an artificial neural network. So for that artificial neural network, I'll be having one cost function, right? Now I'm denoting my cost function as summation of I is equal to 1 to n loss of yi comma yi hat. Okay, this is basically my cost function. Okay, now the regularization is applied on this cost function. Okay, basically the regularization is applied on the cost function. Okay, now to this cost function I will be adding one penalty term. Okay, now by adding this penalty term, your cost function changes. Okay, now let's see what actually is this penalty term, and by adding this penalty term, how my cost function changes. Now how, due to this change in cost function, my weight values changes. Okay, Now this penalty term is nothing but lambda by 2n summation of I is equal to 1 to k modulus of wi whole square. Okay, this is the penalty term. I'll be adding to the cost function so that my weight values will be diminished. Okay, now in this term you may have various doubts that what actually is this lambda value and what actually is this n and what actually is this k, and by adding this term how I am able to decrease the values of the weights. Okay, now let's basically see what are actually this this new variables. Okay, now the lambda is nothing but hyperparameter. Lambda is hyperparameter. Okay, first I'll be writing all the notations and then I'll be explaining one by one. Okay, this n is nothing but number of rows and k is nothing but number of columns. Right, now this lambda is hyperparameter. Now if I set this lambda value to 0, that is lambda is equal to 0. Okay, now 0 by anything is nothing but 0. Now 0 into this entire term becomes 0. So that means if I set this lambda value to 0, I am applying no regularization. Okay, now if I set this lambda value very much higher, it specifies that I am applying very much strong regularization. Okay, now by applying very much strong regularization, what actually happens is we face the problem of underfitting. Okay, so the lambda value must be anything from 0 to some higher numerical value. Okay, it must be from 0 to higher numerical value. Okay, this is basically the meaning of lambda. Okay, now the n is number of rows. Okay, number of rows in the entire data set. Okay, the n value determines the number of rows in the entire data set, and k is nothing but number of columns, that is total number of features in my data. Okay, if I have 10 features in my data, so k value is nothing but 10. Okay, now let me explain with an example. Yeah, c is equal to loss. Okay, c is equal to loss plus uh, summation of I is equal to, so I am taking k value as 10. Okay, k value as 10, so it becomes lambda by 2n summation of modulus of I whole square. Okay, now when I choose the k value as 10, this is my transform term. Okay, this is nothing but the cost. Okay, this is nothing but the cost, and this is c dash. Okay, after applying the regularization, I'm getting the cost function, that is c dash, and this is my actual cost function. Okay, now I'm choosing the k value as 10, so that is why the summation of I is equal to 1 to 10, and this is how we apply regularization. Now let's expand this term. Okay, it becomes lambda by 2n modulus of w1 square plus modulus of w2 square plus so on up to modulus of w10 square. Now in this way you apply regularization. Okay, now by applying this regularization, the weight values, okay, the weight values will be nearly 0. Okay, any weight value, okay, it may be around 5, 6, 10, anything, it will become closer to 0. Okay, that is around 0.5 or 0.1. So these values are transformed to lower numerical values. Now in the next section of the video, let us discuss how by adding this term, okay, how by adding this regularization term, my weight values are diminished closer to 0. Now let's just basically see how by applying regularization my weight values are tending to 0. Okay, now first let me consider my weight updation formula, that is W naught new is equal to W naught old plus learning rate dou L dash by dou W naught old. Okay, this is basically my weight updation formula for regularization. Okay, now this L dash represents, L dash is equal to loss plus lambda by 2n. Okay, loss plus regularization term. Okay, loss plus regularization term represents L dash. Okay, that is summation of I is equal to 0 to k modulus of wi whole square. Okay, this is basically L dash, that is loss after regularization. Now let me do partial differentiation for this loss. Okay, that is do L dash with respect to w naught. I am doing the partial differentiation with respect to w naught. Okay, w naught old is equal to L plus w naught old plus lambda by 2n dou by dou w naught old summation of I is equal to 1 to 0 to k modulus of wi whole square. Now I'll be taking here two assumptions, that is n is equal to 1. Let me say in my entire data set I have only one row. Okay, and k is equal to 5. Okay, n is equal to 1 and k is equal to 5. Now dou L dash by dou w naught old is equal to dou L by dou w naught, just a second, sorry, w naught old plus lambda by 2. Okay, as n is equal to 1, lambda by 2. Okay, now I'm differentiating with respect to w naught. Okay, I'm differentiating with respect to w naught, means my entire terms, okay, entire weight values other than w naught becomes 0. Okay, now dou w naught square by dou w naught old. Okay, dou w naught square by dou w naught old is equal to 2 w naught old. Right, now I becomes 1, that is dou w naught old with respect to dou 1 old square. Okay, what it becomes 0, right? Now so that is why I have written this as in this way. Okay, my 2 and 2 gets cancelled and this finally becomes my dou w naught old is equal to dou L by dou w naught old plus lambda into dou w naught old. Okay, my rest of the weight values has become 0 because I am doing the partial derivative and I am differentiating with respect to w naught, so that is why only w naught is remained over here. Okay, now what I am doing is I am replacing this entire term. Okay, I am replacing this entire term with this. Okay, I am replacing this entire term with respect to these two terms. Okay, now my w naught new becomes learning rate dou L by dou w naught old plus lambda into w naught old. Okay, now I'm multiplying my learning rate inside this square bracket, inside this brackets. Okay, plus actually it's minus, sorry, I'm sorry, actually it's minus, sorry, yeah, actually it's minus, it's my mistake. Okay, so w naught old minus learning rate dou L by dou w naught old minus n into lambda dou w naught old. Okay, now what I am doing is I am taking common from this two terms. Okay, I am taking common from both these terms, that is w naught old. Okay, this becomes w naught old into 1 minus n lambda minus learning rate dou L by dou w naught old. Okay, now this is my w naught new. Okay, this is my entire w naught new. Yeah, now when you keenly observe over here, my learning rate is always from 0 to 1, right? Okay, it's always from 0 to 1, means this is positive quantity. Okay, my lambda value is also from 0 to 1, means it is positive quantity. Okay, now positive into positive, and both these are some smaller numerical values. Okay, my learning rate generally is from 0.1 or 0.001 or 0.0001. Okay, in this way I'm representing my learning rate. Okay, my lambda value is 0.1 or either 0.001 or 0.0001. Okay, in this way I represent lambda. Okay, now when I multiply both these quantities, both the smaller quantities, the resultant quantity will be also much smaller. So when I subtract 1 minus that smaller quantity, I'll be getting another quantity which is also less than 0. Sorry, which is also less than 1, right? Okay, let's say I'm getting around 0.5. Okay, just I'm taking an assumption that I'm subtracting 0.5 from this. Okay, the resultant of both this multiplication is 0.5 and I'm subtracting 1 minus 0.5 and I got around 0.5. Okay, now when you observe over here, this is my old weight value. Okay, this is my old weight value. Now I'm multiplying 0.5 into this old weight value. Means what actually is happening over here, I'm scaling it. Okay, I'm scaling my weight value. Okay, I'm scaling my weight value. Means I'm just taking 50% of my old weight value to update my new weight value. Okay, I'm taking 50% of this. Okay, I'm taking 50% of my old weight value to update my new weight value. Okay, so by applying this regularization, what actually is happening is this scaling. Okay, this scaling term is multiplied to my old weight value. Okay, now this quantity becomes some smaller quantity. Okay, when you compare both this, okay, when you compare both this quantity is larger and this quantity is smaller. Okay, because I'm multiplying 0.5. Okay, because of due to multiplication of 0.5, when compared to this updated weight value, okay, this updated old weight value becomes smaller one. Okay, now when I subtract from the smaller weight value this quantity, okay, this term, it becomes another smaller value. Okay, so in this way my updated weight values are tending to 0. Okay, this is entirely the intuition of regularization. Okay, now let me summarize once. Okay, this is my weight updation formula. Okay, I'm doing with respect to regularization, so that is why I have written L dash over here. Okay, now this is my L dash formula. Okay, L plus regularization term. Okay, now I'm differentiating with respect to W naught weight. Okay, this is my entire partial differentiation and my final partial differentiation, that is dou L dash by dou W naught old is this term. Okay, now instead of this term I'm replacing this both these terms. Okay, now the final representation becomes in this way. Okay, now what I am doing is I'm taking common of W naught old. Okay, now when I take W naught old as common, I'll be getting 1 minus n lambda. Okay, this n and lambda are smaller quantities and positive quantities, so I'll be getting some smaller positive quantity. Okay, as I'm subtracting this smaller and positive quantity from 1, so the resultant quantity is always less than 1. Okay, means I'm multiplying the smaller quantity, okay, resultant smaller quantity, that is scaling term. Okay, that is scaling term with this old weight value. Okay, so this updated weight value, okay, after multiplying this entire term, that is scaling term, with this old weight value, I'll be getting another updated weight value that is smaller. Okay, that is smaller when compared to this. Okay, that will be smaller when compared to this, right? Now after doing this entire calculation, I'll be getting some weight value. Okay, now I'm subtracting n lambda, okay, n dou L by dou W naught all. Okay, this entire gradient term from this weight value. Okay, so the resultant updated W naught new value will be nearly equal to 0. Okay, after this entire process, my updated new weight value will be nearly equal to 0 but not exact 0. Okay, from where we have started from higher weight value. Okay, overfitting problem, higher weight value, and by applying regularization and after this entire calculation, we have come down to closer to 0. Okay, from higher weight value to closer to 0. Okay, because of weights becoming closer to 0, the regularization solves the problem of overfitting. Okay, this is the entire process of regularization. Okay, now in L1 regularization, what happens is just this square term is eliminated. Okay, entirely this square term is eliminated. Now due to elimination of the square term, what actually happens in this regularization is L1 regularization is most of the weight values become 0. Okay, due to this what actually happens, most of the nodes are eliminated. So due to this elimination of the nodes, most of the information is lost. Okay, this is a major drawback in L1 regularization. So that is why in most of the deep learning scenarios we use L2 regularization. Okay, now in the next section of the video we'll be applying L2 regularization to an overfitting problem.
In the previous section of the video, we have clearly seen how overfitting problem can be solved with the help of L2 regularization. Now, in this section of the video, we'll be seeing how by applying L2 regularization on a dataset or on a model, we can solve the problem of overfitting. Okay, now for that, these are the necessary libraries I am considering, and this is my sample dataset that I have already used in the previous video. Okay, this is a randomly generated dataset, not any pre-processed dataset. Okay, this dataset contains around 1000 rows of data and 3 input features. Okay, this is my entirely random generated dataset. Now I am splitting my data into training and testing. Okay, in my training I am giving 80% of the data, whereas in testing I am giving 20% of the data. Okay, after that I am doing the conversion from numpy to tensors. Okay, now after conversion from numpy to tensors, I am converting from tensors to float data type. Okay, this is my entire type conversion. Okay, now I am building my model. Okay, this is my deeper artificial neural network. Okay, after model building, I am defining my loss function, that is mean squared error loss function. As it is a regression dataset, I am using mean squared error loss function and choosing optimizer as Adam optimizer with learning rate 0.001. Okay, now I am training for 700 epochs. Okay, now this is entire my training loop and this is my testing loop. Okay, these are my model results. Okay, after 700 epochs, my training loss is 0.15, whereas my test loss is 0.32. You can see that almost double the train loss. My test loss is almost double the train loss. Means there is clear problem of overfitting. Okay, you can see that due to this huge difference in the train loss and test loss, we can make a conclusion that we are facing the problem of overfitting. Now what we will be doing is we will be making few changes in the code so that we can overcome the problem of overfitting. Okay, now what are the necessary changes is I am again redefining my loss function and optimizer. Okay, this is my redefined loss function and this is my redefined optimizer. Okay, now by adding one small piece of code in my optimizer, I can overcome this problem of overfitting. Okay, now what's that parameter is weight decay. Okay, by adding weight decay, okay, by adding weight decay parameter in optimizer, we can overcome the problem of overfitting. Okay, this weight decay represents L2 regularization. Okay, this weight decay represents we are applying L2 regularization on our dataset. Okay, now weight decay is equal to 0.1. Okay, now this 0.1 and this numerical values, okay, basically this weight decay numerical values are based on the overfitting. Okay, if you face stronger overfitting, then we need to apply stronger regularization. Okay, stronger regularization means the numerical values must be basically 0.1 or 0.001. Okay, now in the case where we see a medium level of overfitting, okay, we need to take weight decay value as 0.001. Okay, where we see less amount of overfitting, we need to apply weaker regularization. So we need to take 0.0001 as weight decay. Okay, this is how we apply L2 regularization to prevent the problem of overfitting. Now I am running my cells after applying the weight decay. Okay, now this is entire my training loop and this is my testing loop. I am printing the model results for every 100 epochs, and you can see that after applying weight decay, that is L2 regularization, you can see that my training loss is around 0.24 and my test loss is 0.25. You can see that there is clear difference. Okay, there is clear difference of around 0.1, okay, 0.01, okay, there's clear difference of 0.01. So in this way we are preventing the problem of overfitting. Okay, you can see that here we have around 0.15 difference, and here we are having 0.01 difference between train loss and test loss. Means how well your model is performing on the training data, that well it is performing on the test data as well. Okay, so in this way we have solved the problem of overfitting. Okay, I'll be providing this entire notebook in the description, so you can check it out or try few hyperparameter tuning. Okay, this is the entire intuition of L2 regularization and how L2 regularization solve the problem of overfitting. Hope you guys like the video. If you like the video, please consider like, sharing and subscribing my channel. Thank you.